Hello, everyone. So let's start the sixth lecture. So today we are going to continue the interprocess communication to talk about the interprocess communication primitives. In particular, we are going to talk about sockets, which allow two applications to communicate over the network. And then we are going to start talking about concurrency. And this will be a pretty long topic, which will go over the next couple of lectures. As always, if you have any questions, please ask in the Q&A thread, or I'll try also to check on the chat. Let's start. So again, like we discussed earlier in this class, today a lot of applications are distributed, right? They are not only running on a single machine on your laptop, but most of them, they have a backend. You need to go over the network in order to implement almost any functionality of the application. And the example, your web browser is a great example. And anything you are using today, almost like many of the applications like Facebook, Twitter, and Google application like Google Docs and obviously Google itself, they look this way. You have a piece of code running on the client side, on your machine, on your phone, and a bigger piece of code which runs on the backend on a bunch of servers in a data centers. And typically all these applications in general looks like that, like this. The client sends a request and it gets a reply back. Okay, the request can be a query in Google. The reply can be the answers to it can be the reply to your search query. For something like Netflix, the reply will be, the request will be your clicks, selecting a movie. The reply can be also a recommendation of other movies, or the movies start streaming, and things like that. Okay, and typically you have more than one client talking with the same server or the same machine. And like, for instance, you have many web clients, and many of them are talking with the same web server. So this is a kind of pattern, communication pattern we have to implement under the hood. So here it's about how also a little bit more details about how client and the server are similar, and even more importantly, how they are different. So the client, again, sends a request like get index HTML, right? This basically specified to get the content of the web page of a site, of the first web page of a site, to render on your machine. And in order to do that, you need to contact a server which stores the index.html, this file, the content of the page you want to render on your machine. And one thing obviously you need to do is that when we need to know is the address of that server, right? It's like when you make a call, you need to know the number you are calling. Okay, so keep in mind that. So you need to know the address of the server from which you get the content. Now, the server, it's typically always on. It has always to be ready to receive requests and answer this request. Unlike, on the other hand, obviously the client is not always on. Your phone, your computer, your laptop is not always on. Most of the time it's actually off. But when it's on, it's going to send this request to a server which should be on all the time in order for you to get the reply right away. Okay. And obviously the clients initiate the contact with the server, not the other way around. So the client doesn't need to know to have a, because of that, the client doesn't need to have a well-known address, but the server has to. Okay. Okay, and like we said before, when the server gets a request, it's going to answer something back, hopefully satisfying the reply, answering the reply according to the user expectations. Okay. So again, we need to send data over the network. Okay. And how do we do that? Well, what we do that, we are going to send some bytes, right? Data consists of bits. We aggregate each 8 bits, it's a 1 byte, right? So typically you measure in bytes, like memory. You also typically measure in bytes or maybe words, which is a bunch of bytes. And more than that is not only we have individual bytes, we have stream of bytes, right? Remember, the stream of bytes is the same interface, the high-level interface from the file systems, okay? And here we are going to talk more about networking later in the lecture, but here we are talking about TCP connections. TCP stands for Transport Control Protocol. Do you know what is the other type of protocol, the common protocol? Besides TCP? Yep, UDP. What does UDP stands for? And ICMP. HTTP is a protocol, but it's at a higher level. It's on top of the TCP. UDP, yes, it's user datagram protocol, not unified user datagram protocol. And HTTP and FTP are also protocols, but they are the higher levels. They are running on top of TCP. Again, we are going to learn. The network software is organized in stacks, in a bunch of layers. And here we are going to talk about the transport layer, and TCP and UDP are at the transport layer. Okay? Yes. So thanks for your answers. Okay, so now we need to abstract the connection between two endpoints, A and B. And the way we are going to do that, it should be, again, be very natural because you are going to send a stream of bytes. You need to abstract like a queue, right? Why a queue? Because, for instance, a very simple example, what happens if the client sends faster than the server can receive, or the server, for some reason, is doing something else and it cannot get the data sent to it right away. This data, it's either is lost, or if you don't want to lose it, you need to buffer somewhere, right? So you have to have a queue, right? And you need to have both from the client to the server and from the server to the client, because both of them, they are going to send data. One of them is going to send typically request, and the other one replies to the request. And now, okay, but what is the abstraction, right? This is kind of, how do we manipulate this kind of connection? And remember that one of the big things about Unix is that everything looks like a file, right? Or it's abstract, it's very similar abstractions. So the same is true for communication, like we saw for pipes last time. Pipes, again, are how you communicate between two processes on the same machine. Here, sockets about how do two processes on different machines communicate with each other. But they are very similar. The abstraction is very similar, and it's looking like a file. And this kind of abstraction for communication is called a socket, right? Okay. So this is how you do it, right? If you want to send some data, the process, the sender, the client, call a write system function call, which passes a descriptor. This is a socket descriptor, a buffer, and the length of the buffer. And the receiver or the server, it's calling the read operation with the file descriptor and a buffer where it can receive the data and the size of the buffer. So to make sure that if it's more data, the operating system doesn't overflow that buffer, right? Okay, so the sockets is an endpoint of communication, right? And the queues are in between here, you know, somewhere along. Actually, there are many queues in the network. There are queues in the operating system, queues as the routers along the path between the sender and the receiver. It's pretty complicated. We are going to learn more about that. But in general, you know, the things for you to know is that there are queues, and there are queues. One of the simplest reasons, one of simpler motivation for queues is to, again, because the client or the two endpoints, they don't have the same speed sending and receiving. So if you receive at a lower speed, then you need to buffer the data, or that the receiver at that time maybe is doing something else, and he cannot receive the data right away. Okay, so now the sockets, you have two sockets connected over the network, one of the sender and one the receiver, or one socket for each endpoint. And now the sockets, you remember, what do you do with sockets, right? It's like, what is a pattern, programming pattern? You open, you read, write, right? If you have a file descriptor, right? You open the file descriptor, you read, write from the file descriptor, and then you close the file descriptor, right? So we need to learn about how to open and close also these sockets, okay? Let me see. Here is a question. Is a communication between two processes actually communication between the thread of the processes? So this is, so anyone wants to answer that question? So the communication, is between two processes, okay? But remember, the process is a container, right? You have the address space, and it provides you protection. But the actual unit of execution or concurrency is a thread. So each process has at least one thread. So it's correct to say that two processes communicate, but it's correct to say that always two threads communicate, because the things which are going to run the code inside this process are the threads. Okay. Typically, when you have one thread and one process, you just interchangeable. You can use, process or thread, but hopefully that answers the question. Okay. It is a hidden abstraction for socket IO. Yeah, what we are going to talk about here, it's pretty much, at least in the next couple of slides, about actually is how you are going to use a socket interface, right? So, okay, oops. Okay, so like we discussed, the socket is an abstraction for one endpoint of the network. If you have in general, you have two processes, two endpoints communicate with each other. Each of them is going to have a socket, and somehow you need to connect these two sockets to each other if you want to establish a connection. And it was introduced first in Berkeley Standard Distribution version 4.2. That is one of the biggest contributions of actually open source contribution of Berkeley, because it has huge impact. And the story here is that the runners, like during those days, you distribute these operating systems through tapes, okay? And so the things here is that it's about how you are going to then there are people waiting in line for the tapes to be copied, and therefore to take it back to their companies to install the new version of Unix. to which with this kind of TCP/IP code in it. And this is a beautiful thing, is that this is a local, again, is like it's the abstraction for a lot of kind of networks type of. When I say a lot of kind of networks, I'm talking about almost about how they are physically implemented. They are over fiber, they are over satellite, cellular networks. So it abstracts away what kind of your application on your iPhone. It doesn't know that you are on a cellular network, right? Or you are Wi-Fi, right? It doesn't know. That means abstraction in that case. And or there are also about how packets are routed in the network and many other things, lower level of the network stack. This was Apple Talk and IPX. So and the great thing about this TCP/IP, it becomes a de facto standard of how nodes communicate over the internet, right? This is what enables the internet at the end of the day. And again, when I say de facto standard, I say because it was a piece of code. It was not a standard body to create it, but of course it's a standard now because everyone is using it. If you don't use TCP/IP, you cannot talk with other nodes in the internet. Okay. So the sockets, of course, you'll see it's a little bit more elaborated interface, but at the end of the day, you need to create a socket. You can close a socket. In between, you read and write. Now, everything is a file descriptor, like we discussed, but also, if you remember, like we discussed, although you have, everything is file descriptor, you don't have, for each device, you don't have all the commands like you have for file systems, right? For file system, you have a seek, right? You can reposition the pointer from where to read in a particular file. I can lseek and I can read from the 100th bytes in the file, right? It's still the abstraction is still a stream of bytes, right? But I can reposition. Here you cannot have seek, right? You send the bytes and you receive in the same order. It is kind of strange. Will be, oh, I want to read the 100 bytes, right? Maybe that 100 byte is not even, your computer haven't received it. Okay, so you don't have lseek. Your abstraction is just a queue, right? First in, first out. You always get the data in the order in which is sent. The other thing, what happens is under the hood, it's abstracted away, is that you don't, over the network, you don't send a stream of bytes, right? You actually put it in packages, you package it. You divide the data you have to send, you package it in a packet. And each packet will have addresses, right? Because, and then this tells the network where the packet should be delivered, right? It's like, you put, Amazon is using trucks, and each truck now says an address, the driver, where it should deliver the packages, right? Something like that. They may need also some kind of like RPC kind of facility to, for instance, because the data format which is understood by the receiver is not as the same as the data format which is understood by the sender, right? And you'll talk about this is, big Indian, little Indian kind of different formats, for different processors, right? Okay, so this is a very simple example. Echo server, hello world. Echo means, I am sending a message to the server is going to send me the message back, right? So here is how things are happening, right? You have a client on the left-hand side, server on the right-hand side, and you have with this also the data points. The time here goes from top to the bottom, and you have this kind of green rectangles shows about the lifetime of a socket, both on the client side and the server side. A socket starts with being open and closed, right? Okay. So once you open and close the the socket, the server should be ready to receive data. What the server is doing then, well, is calling a read system command on the corresponding socket descriptor of that connection and provide a buffer where the operating system should pass the data it receives. Okay. The client say it do a fgets to get from the standard input from, you can type the message and we want to send that message, right? How you send the message, like we discussed, you call a write, right? And you pass the socket file descriptors on from the same communication, and on the sender side, on the client side, and you pass the buffer you want to send out, right? Now, and then you want to read back, right? Notice that both the reads are blocking in this particular case. There are variants of reads calls which are not blocking, but here we are, by default we assume is blocking. We need to block until you get some data, right? So the client writes a message and then waits to get some a reply back. That message may be chopped in different packets. The packets are sent over the internet. Actually, each packet can take a different path, and the server gets the data. Maybe writes, show it on the screen. Is doing some printfs or something like that, and then you write it back to the socket. So you want to send it back to the client, and the client, the read, it's again was waiting into a read call, is going to get the message back and is going to print on the screen. Again, the same message. We are talking here about an echo server, right? Like echo application. Okay. Let me see. Seems there's another question. RPC, what it stands, Danny asked about, what does RPC stands for? RPC stands for Remote Procedure Call. This is a higher level, and again, we'll learn about it. And we just mentioned a little bit about it in a previous lecture. But this is about, think about, you want to call a function, and that function, instead of executing locally, it's executing on a different machine. And you want to just the syntax and ideally the semantics, although we learned that that's not really possible, to be very similar with invoking a local function call. So you want how you invoke a local function, a remote function, to look very similar with how you invoke a local function. Okay, so RPC tries to bridge that gap and make them very similar. Okay. Okay. Let's. We have a bunch of code here, and I'm not going to go through every line of code. We don't have time, and we'll try to cover as much as possible. So, but I'm saying that if I'm not going, and maybe you have questions, please ask me. But it's not my intention to go through each line. Okay, so this is about, for the previous examples, how the code look like, right? So this is typically how the code look like, right? It's like, and this is the cloud client. You are in the while loop. You get some message typed by the user, and you send it to the server. The server sends it back, and you print it, right? This is what you do. You get the message. You write to the socket. You read it back, and you you print it out. And before you read it back, you clear the buffer, so you know that it's not the message you just send, it's just in the buffer. You clear it to know that what you have in the buffer is what you receive from the server. And the server is very similar. You read, and then, yeah. I think it's a mistake in this code. This should be if len less than 0. So this is how much you read. And if len is less than 0, this means that it's an error. Okay. If len is greater than 0, so this len, actually, let me just try to Okay. Okay. So you read it, the server reads data from the socket. If it's less than 0, it's an error. You return. Greater than 0, you print it to the terminal, and then you send it back to the client, right? You echo what you got from the client, right? So this is a send, right, from the client, and the corresponding receive from the server, and this is a corresponding send from the server, and the corresponding receive from the client. Okay, very simple. So now we are making some assumptions, which are actually, this is, in some sense, the assumption we are making here is about what is a networking field about. It's about how to ensure that these assumptions are true, are standing. So one of the assumptions we make is that the data when you is not lost, right? You send it over the network, and the receiver gets all the data that the sender sent, right? It's like a local pipe, right? But this is difficult because internet is probably the biggest and the most complex system that humans build in some sense, and there are many things can go wrong in between. So making, providing to the applications that no matter what happens under the hood in the network, the data which is sent by the client gets to the server without being lost is not easy fit. The other thing you have is that it's, again, remember, this is the abstraction. It's a stream. The data abstraction is a stream. So this means that the order in which you send the data is the order in which the receiver gets the data. Okay. If you write X and write Y, then the receiver reads first X and then gets Y, right? Okay. When you ask for a read, you get what it's ever at that time. So basically, say you if you write, for instance, so this is very important. So if you write, say, 1,000 bytes, actually the receiver can get can get it in bunch of 100 bytes, right? So if you get every time 100 bytes, you need to read 10 times to get the entire content, right? If nothing it's arrived after it's on the connection, you are blocking like we discussed, and yeah, so the semantic is pretty much like pipes, but now it's over the network instead of a single node. Now, so where things getting more interesting, it's about how do you create these sockets, right? And basically, it's you need to if you think about with files, it's simple, right? With files, you have a name and of the file, and you open that the file with that particular name, and that's independent of the processes. Okay, so easy to name, right? How do you do in pipes? Do you remember how do you do in pipes? How does, for instance, when and well, I guess it's the slide is already saying, but how do you do it with pipes? Pipes is, again, the pipes processes runs on the same machine. So if you are going to communicate between the parent and the child, then it's easy, right? Because the child, remember, inherits all the file descriptors of the parent. So already know the file descriptors corresponding to a pipe. Okay, so now with the sockets, there are two things. One, unlike a pipe, if you remember, it's one-way communication. With sockets, you have two-way communication, right? You need both the sender and the receiver being able to send data to each other, right? You'll see a little bit why is that, and the processes are separate, right? Are on different machines. So they cannot communicate otherwise. So how can they agree, or how do I know to what other process I need to communicate, right? And so that's kind of is a crux of the problem. It's a naming. Okay. So how do two independent programs know how to talk with each other? And again, we discussed a little bit about at the beginning of the class, but in the internet, the way you are going to name, it's basically using these DNS names, right? And this is an example. Again, we are going to have a lecture. We are going to talk more about that, but for now is www.ecs.berkeley.edu, right? You have a domain name edu, and then it's a top domain, and then Berkeley is an institution, then it's a department, and this is a protocol. This application level protocol. Again, TCP and IP, TCP and UDP are transport level protocols. But then under the hood is a transport level. This is what application knows. This is what you can type in the browser, right? www.google.com, right? This is what application understands. The transport layer, the TCP doesn't understand this. What understands are IP addresses. And there is a way, is DNS name resolution, by which these DNS names or the host names are translated into these IP addresses. Okay? But when we are going to operate at this level, typically we are going to operate with the IP addresses. Okay? And an IP address, it used to have 32 bits. It still have in many parts of the world, and it's still dominant. And this is IPv4. IPv4 is IP stands for Internet Protocol, V4, version 4, 32 bits. This was from the beginning of the internet. But then we ran out of addresses because IPv4, you have 32 bits, so you can have only 4 billion addresses. And then now we have IPv6, and it took probably 20 or more years to start and to kind of get up to speed with the transition from IPv4 and IPv6. And IPv6 has 128 bits, a lot of bits. We won't run out of them. Now, in addition to the addresses, you have what are called port numbers. Okay, and I mean, probably there are people here who took networking. So can anyone answer why do we need a port number? What is a port number? Yes, Alison, very good. So multiple services run on the same host. So it's very simple. These IP addresses name a host, name a computer, name a machine. But a machine, like we know, runs multiple processes. And your code to receive data runs in one of these processes. Okay? So you don't need only to identify a host. You also need to identify the process to which you are going to send out. And from the network perspective, that process is identified by a port number, right? It's not identified, it's not by outside the computer, it's not identified by the process ID, it's by this port number, okay? Port numbers has to 16 bits. And the first bits, the first 1023 ports are well known, meaning that they are well-known services. What does it mean? 80. Port 80 is typically for web browser. So if you have, if you put 80, then it's typically a web browser listen on the port 80 to get all the packets which are coming to that host, and they say they are looking for port 80. Okay. Okay. So now, when you have a server, right? And remember what we have this figure early on, we have multiple clients talking with the server. Okay. So how does a server can talk with multiple clients? How does it know which packets come from which client? That's a problem, right? So the way we take care of that is very simple. The server doesn't communicate with each client. The server only waits from each client to connect. And when it connects, the server creates another process which communicate to the client. Okay? So that's kind of the idea. We are going to reiterate on this idea, so hopefully it will be clear by the end of this lecture. But that's what happened. That's a pattern. So the client creates a socket and connects the server. Request, but again, it doesn't send just a message, a request. Oh, I have the request, give me a reply. The client sends a connection request to create a connection first. And only after he has a connection, you can send, sorry, you are going to send the data and your request. The server listens. It's in the state of always listens for new connections, accepts the connection, and now it creates a new socket. Okay, this socket can be in a different process or can be in a different thread in the same process. We'll see that. Okay, so now you have a connection socket for this client, and now you are going to send information about this connection socket, and you establish now a connection between the client socket and a socket on the server side, which is special for that client, right? So this is what happens, right? So each connection, this yellow thing here, right? Between these two green bubbles, it's identified by 5 things: source IP address, destination IP address, right? These are the source and the destination. The destination. When you send a packet, you have the source IP address of machine, the IP address of the machine who sends that packet, and the destination IP address, the IP address of the receiver machine, right? Then you have the port numbers. Is the port numbers of the process who sent the data, and then the destination port number, the port number of the process who receives the data, and then your protocol type. Now here, the protocol type, it's TCP in this lecture, but like we discussed also, you can have UDP, user datagram protocol. Okay, let me see, it's another question. Oh, I think probably I missed this. Akshit asked this question. Isn't this also a problem for processes on the same computer? How will one identify the other? PID. So basically about how do I identify the processes? So yes, so depends. So on the same machine, the problem is not about only how do I identify, but how you are sharing the identification. Okay. For instance, on a machine, yes, you have access to the PID and you can identify everything by PID on the same machine, right? And if you want to make a PID to let one process know about the identifier of another process, there are many ways to do it, right? One way, simple way, is to write that in a file, right? Basically, you have like the equivalent of a server on your machine, and you want to know, say, the PID of that one. You always, when you start that server on that machine, you write the PID in a file, right? So that one. But by the way, the one important thing to note is that while here I am always repeating and repeating and repeating that the sender and the receivers are on two different nodes, they can also be on the same machine, and it's going to work, right? So you can use TCP to communicate between two processes on the same machine. Okay, no problem. Yes. Okay. Good. So in order to know the server, what do you need to know, right? So again, you need to know about its IP address and then the port numbers on which this server is listening. And typically, again, the well-known services, they have well-known ports, like port 80 and, send mail is 25 and things like that, right? And this is well-known means that everyone knows it. If it's an web server running on one machine with this address, that web server will run on port 80. Okay, so now let's go a little bit more details about how things are happening to see how these new connections are created. So the server, you create a socket and you bind it to a local address, to an address, which is a local address of the machine typically, and a port, right? So if you web server, you bind it to port 80. And then you listen for connection from the clients. You get a connection, you accept it, right? And now let's move to the client. On the client side, I create a socket, and then I connect to the server specifying the host IP address and the port number. And it's a host and the port number to is the server host binded. Right? This is a little bit the pattern we saw before. You send a client, send a connection request to the server which was listening, and the server accept and send back accept calls. And now a new and creates also a socket the server, and now you have a connection. Now the server goes to read into read, blocks into a read, and the client writes. So eventually when the data written by the client gets to the server reads it and writes a response. The client reads the response, and then at the end, you close the socket, right? So if you can see about everyone is closing the socket, both the client and the server, and the client has created the socket. This is equivalent to an open, and the equivalent socket, which is the server, creates two sockets, one on which is listening for requests for new connections. And then when it's going to accept a request for connection, is going to create a socket for that connection. Okay, so accept syscall is going to create a socket for that connection. The connection, corresponding to the connection request from the client. Okay. Here is a question. How do you have multiple web servers on the same machine? There is only one port? So typically you don't have multiple web servers on the same machine. If you want to have multiple web servers on the same machine, you have to assign them to different numbers. And by these web numbers, you need to tell other clients what the new port numbers are. Like for instance, typically another port number web server use, if it's not 80, it's 8080. Oh, I didn't say that, but this is a well-known port number from 0 to 1 to 1023. You can only bind them if you are you have root privileges, right? If you are just user, you cannot bind on these ports. And so if you want to run the web server only as a user, typically people put 8080, the port number. Okay, a few questions here. Another question. No, okay, I answered the question, sorry. Pipes are one way. You need to create two pipes, you want to communicate both ways. Yeah. And there is another answer for Allison. If you have multiple websites on the same server, you can do it at the application layer. HTTP request has a host header, which tells the server, hey, I want to talk to X site, and the server can just send back the right site. Well, that's a little bit more complicated. And I guess everything is possible in software. But typically this is, yeah, you can have the content distribution networks. They do something like you propose here. We'll talk a little bit about that later. But for now, if you, again, the one thing to know is that if you really want to run multiple web servers on the same host, you need to provide different port numbers. This is a client protocol, a little bit in more details. This is how you create the socket, right? Remember, and when you create the socket, first of all, you create this kind of address info data structure where you provide the host name and the port name, okay? And then you create the socket by using this data structure you just created, and it has 3 things. Typically, you can add more. Address family, you basically, this is whether it's IPv4, IPv6, or something else that are. You can have socket type. You have socket stream. It's a typo here. It's a sock stream or sock datagram. Socket stream, this is a stream of bytes. The datagram, right, is something we are not discussing, which is in UDP. In UDP, you don't send a stream of bytes, you send packets, okay? And then you have this also TCP. It's this is a protocol type, so this can be like TCP. 0, you can have any protocol. Then you connect. This is a connection request, and you say, you know, you define the server address and the port number, and then you run the client code on that file descriptor, socket descriptor, and you close, right? So again, the server here, just to make sure that I didn't say something wrong. The server here, when you do the lookup, you basically provide the host name. This is the server name and the server port number. Okay, this is what you provide in this server. What you do in the server data structure. And for the server protocol, it's a little bit more involved. You create a socket, and you give the port name where you want to bind, to which you want to bind the server, and then you bind the server typically to the local address and the port number. Then you listen for connection requests. And now what you do, you go into a loop, and when you get a connection request, you accept it, you create a socket, this is connect socket, and then you serve the client and you close the socket. And eventually when the server ends, then you also close the server socket, but the server socket is the one on which you are listening, remember. So then, okay, so now you are going to have requests from different clients. We saw that for each request connection, we are going to create a different socket on the server side. Now, where is a code running on the server side going? Where is a code running on the server side going to run? So where is this served client going to run? You see here, right? Where is that going to run? So, and there are multiple ways, multiple methods here. One, if you want to really protect yourself about, the client sending you something stupid, or and you do some bad things, it causes you to do some bad things. You can do it. You can run that code in a separate process. You remember the processes as a unit of protection, right? Processes are protected from each other, right? So in this particular case, right, you have a connection when accept syscall, create a connection socket, and then you are going to create a child, and you are going to answer the client in the child, while the parent doesn't do anything. It maybe waits for the child to finish, right? So this is a code. On the server side, you accept, not all the code, it's only in the while loop. You accept the connection request, then you fork. Remember, if the result of the fork PID is 0, this means that you are here executing what? The child code, the child code, right? So the child is close the server socket. This is a socket on the server, listen for new connections. So the child only needs to reply to the client. So it's not going to listen for new clients, right? And then you serve the client, and you also close the connection to that client, and you exit. And on the server side, on the parent side, which is a server itself, you close the connection socket, because you are not going to communicate directly to that client. The child is going to communicate, and then wait. While the wait is doing, wait for the child to finish, and then at the end you close the server connection, right? So to summarize, in a server, you listen, and for connection request, if there are multiple requests at the same time, they are going to be queued, and then you create connections, and then use this connection to communicate with the child. Okay, and this is a server, because it listens and creates connection for this child, can answer, at the same time can talk at the same time with multiple clients. Okay. So one potential thing here is that in this code, like I said, the parent, this is a parent code in this else, on the else branch, you wait for the child to finish. But if you wait for the child to finish, then you cannot listen and you cannot satisfy other connection requests. So actually, if you write this code, the server, although you have a different process for the connection, you cannot accept new connections. So you are talking with one client at a time. So what is the fix here? Well, the fix is very simple. Don't wait. Go back, don't wait, and go, like if you are a server, go back and accept, be ready to accept new connection requests from new clients. Okay. This is address, how you set up the address. Again, I'm not going to go from so details. You have the same things like, SOC stream is like, it's a data stream. This is what you have for TCP. This is, you don't specify the IP, IP family and things like that. But this is, again, it's a boilerplate code to set up this address information data structure. So this is a boiler. It's from the client side. So this is how you set the address, and how you and this is how you get the address of the server from the client, right? So you get it from, you specify the host name and the port name, and you get the address information. The address information, including the IP address of the server. Okay. Now, so far I said that you can provide concurrency if you run, and for each client, on the server side, you have a different process to talk with that client, right? So now you have concurrency because processes can run concurrently. But now the problem with processes, what it is that they provide protection, but they are heavyweight. If you want to provide concurrency, but more heavyweight, and you are not as concerned about protection, what do? You can use threads, right? The thread, you can have multiple threads in the same process. And now what you are going to do when you are going to accept a connection request from a client and you are creating a socket, you are going to spawn a thread. Okay. But if you spawn a thread, what is the problem right now? This was also in the case of the when you use the processes. What is the problem? Right? See any problem here? Well, what if you have many clients? You know, you can have actually an attack. I can have many clients opening new connections and never closing them, and and this way exhaust resources on the server side. So how do you do that? What is the solution here? Well, the solution here is to create what is called a thread pool. So you create a bunch of threads, say 100 threads, which means that at a given time, you can talk concurrently with 100 clients. What if there are more than 100 clients? Well, they have to wait for some of the current clients you are talking with to finish and release a thread. Okay, so this is a concept, and it's a very useful concept about the thread pool. And the main goal of the thread pool is to protect the resources of the server from being exhausted. Okay, very simple. Okay, and how do you have that? You have here a master thread, and the master thread, this is actually the server, which is going where the code of the server, which is waiting for the connection request, runs. And when you create when you create when you accept a connection request and you create a socket, then you put that you enqueue a request. Now is a request for a thread. You ask for a thread. Okay, this is enqueue to the queue of threads, the connection, right? And you can wake up the queue. The wake up the queue, this is another thread actually, which basically you wake up to run the code. And on the queue side, you are going to look at the connection, you dequeue from the queue, and if the connection if connection is not null, is null, this means there is nothing in the queue, so you just go to sleep. And that's why the master needs to wake you up, right? And else you serve the web page. Okay. So I'm going to have the announcement before then. Let's see what are the other questions. Does this newly created process start listening for new requests as well? No. This is a great question. No, the new created requests do not, and I'm going to show you the code. You see here, again, the new created process, it's a child. And this is a code under the PID equals 0, which is executed by the child. So the first thing the child is doing is closing the server socket. The server socket is the one on which the server listens for new connections. So this tells you, this instruction tells you right away that the child doesn't listen for new connection to be created. The only role of the child is to deal with the connection to the client it was associated to. Okay. Let me see. Yeah, so wait for a thread to join. Yes, if you are, if you create a new thread and you have to wait for the thread to join because the thread is in the process. So if the process goes away, then the thread you created is going to go away, right? So you need, like someone like Christian or Simon said, you need to wait for the thread to join. Let's see. Okay. Oops. Announcement. Project 1, the design documents are due to this Friday. The design reviews are going to happen next week, and keep a lookout on Piazza for signups. You are going to sign with your TA to give, the TA will provide you with a feedback on your design. And the design is something very, very important, design documents, right? You may not have been used with this in other classes, but in this class, before you start writing the first lines of code, you are going to write a design document, at least as a theory. And therefore, it's going to force you to think about the design. And then the idea is that once you have a good design document and you got the feedback, you address the feedback, you'll have a much easier job to write and finish your project, to do your project. Okay. Think more, work less, something like that. By the way, probably it was the people, many of you went, did summer internships at software engineering companies. You know very well that everywhere you need to have a design document before you write the code. So this is great practice for your next job. Even if you do the next thing you are going to do, you do a PhD, still the design documents are great. The homework one is due on Thursday, and the midterm is due in 15 days, 5 to 6 p.m. Oh, it will be 2 weeks from now, 2 weeks from tomorrow. Sorry, and it will be online and proctored, and we'll get more details. We'll get more details next week. Okay. So now for the last 15 minutes, we are going to switch gears and we are going to talk about a very important topic, synchronization. And we are only going to start here about synchronization, concurrency and synchronization. And everything starts from the need to multiplex processes, right? And you need to run multiple activities concurrently. Like we've seen just a few minutes ago, that if we want a server to handle multiple clients at the same time, the way it's doing it, either using processes or multiple threads running at the same time, where each thread or processes is associated with the client. Okay? Good. Now, again, remember for the nth time, right? It's like a process is a unit of protection, right? It has an address space which is protected from other processes. And the processes is represented by the process control block. We talk a little bit about that if you remember. This process control block has all the state that represent that process. In short, if you save that state, then you can restart the process from that state as if nothing had happened. Okay? So what do you have? You have a status. We'll see what is a status, whether the process was running, ready, or blocked. You have some register state when not ready, process ID, some other information like the execution time. Memory space, this is a big one. The memory of the process, right? It has to be somewhere. You need to what memory you are using. You have to know it. Translation, how you translate. Remember, you have virtual memory. The process is a virtual memory, but the data is stored in physical memory. You need to translate between the addresses of the virtual memory to the physical memory. So you need to have this translation table. And again, why do you need to define this control state? It's because this allows, again, the process to switch between processes, right? You give a process, if you save all the state associated in the PCB with the process, and then you can give the CPU to another process to run, and then you can come back to the previous process, and you can restart it from the same place, so to speak, by using all the information in the PCB, right? Okay. Okay, and this is what happens, right? This is how you are going to multiplex, for instance, one CPU between two processes, P0 and P1, right? And this is what you do it, from P0, you want to switch from P0 to P1. The operating system is going to save the state of the P0 in PCB0, right? Then it's going to load the state of process P1 from PCB1. Then it's going to run the process, process P1, and then at some point, when the time quanta for that process P1 expired, or when it's waiting for something, then it's going to do the same thing, but the other way around. It's going to save the PCB1, the state of process P1 in PCB1, and then reload the state of P0 in PCB0, and then resume the execution of P0. Okay, that's all. Right. And this is operating system high level of privilege, meaning that this code cannot be executed by the applications. And all of this yellow stuff, what are those? Function calls, interrupts. Now, you remember that here we are talking about the status of the process in the PCB. Well, this is the status. This is the state, or the state of the process. A process first is created, then is put in the queue if it's ready to execute. From the queue, from being ready to execute, it can go in running state, is ready to run, is running, and can terminate, or it can be interrupted, right? For instance, its time quanta expired, so it's put again back in the ready state, or is doing an IO event, it's doing a read, waiting from some data from the network to get some data from the network, right? So now you are in waiting state. Again, you are no longer running. When you are going to get the data you are waiting for, you are going to be in a ready state, so you can run again, right? Oops. Okay, so we have also the animation. So the process is created, you are going to go into ready state. Here you can run when the processor, when the CPU is available, then you run. You can get an interrupt, like I mentioned, when your time quanta expired, and then do that multiple times, like we saw in the previous slide. You can switch between P0 and P1, right? Then you can, if you execute an IO operation, the process can wait, should wait, no longer running. When the wait ends, because it got the data, for instance, for which it is waiting for, go into a ready state, and you run for a little bit again, and then you are done, exit. Okay, the scheduling, this is just a part, is ready queue. And the scheduling, basically, what is a scheduler? What is the role of the scheduler, right? We talk about the scheduler. The scheduler picks which ready process to run next. Okay, that's it. Okay, and here you see that once you run, there are multiple ways you can stop running. Like I said, time slice expires. You are doing an IO request, and you need to wait for that to complete. You can fork a child, or you can wait for interrupt. Like for instance, yeah, from a timer interrupt, or interrupt from the keyboard, or something like that. Okay, let me see about examples, questions, sorry. Why do we need thread pools? Can we just create thread as request comes? Okay, Philip, so what happens if you have 1 million requests? Each thread actually consumes resources. So therefore, at some point, you exhaust the resources of a machine. And then everything becomes extremely slow. You get thrashing. You want to avoid that. From Miles, assuming one CPU, how does the kernel ensure each process is run smoothly? Is there a timer for when the scheduler interrupts for each PCB? That's correct. This is the one. Time slice expires. So the time slice, you know, the kernels, they typically have, say, 10 milliseconds or 1 milliseconds. So a process or a thread, actually the thread runs. When I say a process, in this case, I am using interchangeably. But the process /thread runs, it can run only up to, say, 10 milliseconds or 1 millisecond. When that expires, the process is swapped out. Okay. Some question. How is a process PCB distinct from the thread control block? The PCB is again contains the state associated with the process, which a lot of more state. Like for instance, the state about the memory, the pages, and the translation. It also contains the file descriptors. Okay. The thread, it's only storing, it's the thread control block. It's only typically registers and the stack, right? It's much smaller. Okay. Hopefully answer the question. Okay. If the process is not running, is PCB, which represents the process in the kernel, is in some scheduler queue, maybe waiting for an IO operation to complete, or waiting for an interrupt, or things like that. Okay. And each queue, again, can have different scheduling policies about how you are going to serve the next PCB from that queue. This is a ready queue. Okay. And here you have this kind of, each node represent one process. You see here the PCB. This is a queue for each device. You can have for the USB, for the disk, Ethernet. This is for networking. So if there is nothing there. Now for the disk, in this case, you have two processes which are waiting to operate, waiting to operate, say read or write on the disk, right? So the kernel will decide what is the order in which they are going to be scheduled. The request is going to be satisfied. Okay, and the same for the network. So the scheduler is actually, the code is very simple. Like this is for the ready process, right? You go to the ready process. If the ready process, if a ready process, so if the queue is not empty, this is what that means. You select the process. This is what from the queue. This is a scheduling operation. And you get the PCB of the next process to schedule. And you run the next PCB. Otherwise, you are idle because there is no process to be scheduled. So the process, like I mentioned, the scheduling is a mechanism for deciding which process or thread to run on the CPU. And there are lots of different scheduling policies. There are thousands, tens of thousands of papers on scheduling policies because there are different properties you want to enforce, maybe fairness between different application or processes, provide real-time guarantees, latency optimizations, and things like that. Okay. And remember that actually the part which is running from a process, it's kind of is a thread. That's the active component. Address space is passive. It's protection. It's just protection. Why have multiple threads per address space? We already know that. We saw that an example. You know, if you can have one thread for each connection for each client. This again is showing you the share state between the thread in the same process and then per thread state, right? It's a thread control block and you have registers, stack information, and that's pretty much it. While the share state, you have global variables, the heap, the memory, the code, and things like that. And the core of the concurrency is this dispatch loop, right? Is a loop. You run the thread, choose the next thread, save the state. This is now is written in terms of the threads at the thread granularity, but this is exactly what this loop in the kernel is doing. You run the current thread, then when that thread terminates or it's interrupted because of timer and so forth, you choose the next thread, right, from the queue. You save the state of the current thread, and you load the state of the new thread, and now you run the new thread. Okay, and this is an infinite loop, right? You never stop. Okay, so let's stop here and let me see any other question. Okay, so no more questions. So let's stop here, like on the dot. Good luck with the homework. Good luck with the project. And let me know if you have any other questions. If not, I'm going to see you all on Thursday. Okay, have a great day.